Okay, so good morning, dear colleagues. So I'm happy to see all of you within our kickoff meeting. So this meeting is devoted to the project entitled Advanced MRI Techniques for Quantitative Assessment of Inflammation and Fibrosis as Diagnostic and Follow-up Markers. It was launched within the 8th Mega Grant funding call in ITMO University in close collaboration with Almazov National Medical Research Center and Dr. David Bendahan from the Center for Magnetic Resonance in Biology and Medicine, University of Aix-Marseille. So my name is Alena Shchelokova, and I'm one of the project participants and will moderate our meeting today. I hope that the hybrid format of our meeting will not hurt to make it productive and interesting for all the participants. And we will have today several presentations, 15 minutes each, including 2-3 questions afterwards. So if you would like to ask a question, please raise your hands, either here or your virtual hand in Zoom. So total meeting duration will be approximately 3 hours, including 1 coffee break in the middle. And after all the talks, we will have a round table where you will be able to ask additional or more detailed questions regarding presentations or exchange their ideas. So now I would like to introduce our first speaker, a leading scientist of the project, Dr. David Bendahan, who is a CNRS research director, the leader of the SIMS, spectroscopy and imaging of the musculoskeletal system group at the Center for Magnetic Resonance in Biology and Medicine of Aix-Marseille University. David has been involved in MRI research for the last 25 years. His initial field of interest was related to MR spectroscopy of metabolic changes in exercises, muscle in humans and animal models of human diseases. 10 years ago, he started to use MRI as an additional tool for functional MR investigation of muscle and MSK disorders. And in 2000, he was awarded bronze medal from the CNRS for achievements in the development of phosphorus MR spectroscopy of exercise and muscle in humans for the investigation of muscle fatigue and overall translation for clinical applications. He has published over 180 peer-reviewed articles, and moreover, David supervises PhD students and postdoc researchers and give lectures to the students at Montpellier University on the topic of assessment of muscle function using MRI and MRS. So I hope I'm not missing something. So David, you're welcome.
Okay, can you hear me?
Yeah, yes, we can hear you.
Okay, so I need to share my screen, I think. So here. Okay, and okay, and here we are. Can you see the screen?
Not yet.
No. Okay. Oh, maybe I need to.
You should put the green button. The screen demonstration.
Oh no, okay. I missed the last step, which is this one. And
yeah, we see your screen, but not presentation.
Okay. And this should be.
Yeah, this should be.
Okay now?
Now, yes, it's okay.
Perfect. Okay, very good. So thank you very much, Alena, for this very kind introduction. So as you said, I would like to say a few words about the project. You gave already the title. I'm going to repeat it. So it's Advanced Magnetic Resonance Imaging Technique for the Quantitative Assessment of Inflammation and Fibrosis as Diagnostic and Follow-up Markers. So as you can see on the slide, there are multiple people involved in the project, and above all, this project has been funded by the mega grant funding application, and I will give you a few words about this mega grant project a little bit later. So I wanted to start with the people involved in this project. So if I can, okay. So as you can see, we wanted to have this project as a collaboration between people from different fields, and this was a very important point in this project. So you can see that at the center, you've got the people from ITMO University and who have a very large expertise of MRI and physics. And so I've been honored to be invited as a leader scientist of this project. And as Alena mentioned to you, I'm a biochemist involved in MRI and MRS for quite a long time. So on the top of this very nice group, we have a close collaboration with the people from Almazov Centre, and this is central for the project because they're going to provide us the expertise not only in MRI but also in the clinical application. And I think the exchange between people involved in physics and people involved in clinical application, this will give us a very nice opportunity to have a project which will be original. And we also have some collaboration with people from my lab in Marseille, CRM, which is funded by CNRS. And I would like to mention Stanislas Rapacchi, who is a CNRS researcher, and he already started to have some exchange with us. And I would like to thank him very much for his involvement. And we'll have also some students from Marseille and also some clinicians involved either in radiology or rheumatology. But this list is not fixed as it is now. So we very much expect that it will be growing up during the course of the project. And so we needed to create some kind of identity for this overall project. And so we called our group QMRI-MA. So you've got the logo appearing on the left edge of the slide. So we already have a logo, which is a good starting point. And you can see that the logo is referring to quantitative MRI for medical application. And I've added the logo of the mega grant staff because I think it's nice to mention people who from the project. So I would like also to give a few words about the mega grant project. So I didn't know a lot about this a few months ago. And for those of you who are not very much aware of that, the mega grant funding is an international cooperation program. And so I've tried to summarize what the mega grant means for the people who are funding. So the mega grant is funding research project. We are supposed to provide some new insight in science. It provides some funding for the creation of competitive research laboratories. So there is also an aspect related to training. So training of qualified scientific staff, but also training of young students. And I think this will be a very important part of the project. So the funding is also here to have some links between international partners, and you have seen that we've got already some connection with Marseille, but we hope we'll have connection with other people from other countries. And of course, the project is also intending to have some kind of transfer between the technologies we are going to develop to the economic sector. So the survey of this grant, you can see it on this slide in terms of numbers. So far, there have been 315 laboratories which have been created thanks to the mega grant, with collaboration with 36 countries and 133 universities and scientific institutions. So this number to say that the mega grant is a very successful funding project. So coming now a little bit to the science. So as you can see from the title, the main aim of the project is to apply advanced techniques of MRI to target some specific clinical applications. So from a general point of view, once you've got a pathological process, clinician would like to have an early diagnosis to be able to measure or quantify the disease activity, and also if there is any therapeutic strategy, they would like to follow the efficiency of the strategy. And in order to do so, everybody in our scientific field is looking for biomarkers which would be as far as possible quantitative, because if they are not, it will be difficult to measure anything. And of course, these biomarkers will have to be sensitive to all these things, sensitive to the disease, sensitive to the changes which can occur throughout a therapy. And of course, they will have to be reliable in order to be used for clinical application, because I need to insist on the fact that we really want to translate all these very advanced techniques to a real clinical application. So in this project, we have spotted so far a few clinical issues, and I've summarized them in this slide. So you can see myocardial inflammation. We are going to work also on cartilage in rheumatoid pathologies. We are also be interested in atrial fibrosis and in chronic heart failure, and most specifically in iron deposition in this pathology. So as I said, what we want to do is to create a link between these clinical manifestations and advanced MRI techniques. So I've summarized here a few of them. I hope we'll be able to create some new, but so far there are multiple tools, MRI quantitative tools, that are available that could give us some nice biomarkers to assess these different pathologies. So for this pathology, we have identified several pathological changes. So I've summarized them in here. So fibrosis, necrosis, inflammation, fat infiltration. So all these things, we would like to be able to measure them specifically in order to be able to follow the changes occurring during these different disorders. And so, as I said, we are going to use quantitative MRI, but with the expertise of our colleague from ITMO University, we will also take advantage of the very nice work they have been doing about RF coils, the new generation of RF coils, the pads, which are coils, but which are passive coils, I would say. So quantitative MRI, I'll give a few words about that. And the project will be also centered not only in the acquisition part, but also in the post-processing part, because we think that combining the new generation coils, the modern advanced technique of acquisition and advanced technique of post-processing, this is the good recipe to have a very nice project and very nice result. So when I've been invited to take part to this project, I thought about the people who were studying the mechanism of the evolution of science. There are people from different centuries, and all of them, the people who are mentioned here, they were talking about science discontinuity. So for them, in order to have a very important progress in science, they were saying that you need to have a kind of break between the different progresses. So in other words, they were saying that science is not going linearly, but at some point you can see some break, and these breaks allowed you really to make a real progress in science. So I have to say that when I've been involved in the project before this one, this project is MCube. This is the project that gave me the opportunity to meet all the people from ITMO University. I was really thinking that I was living science discontinuity, maybe not in terms of real science, but it was a kind of rupture between my main field of interest, which is biology, and the field of interest I was entering. It was MRI and more specifically coils and pads, and also new generation of coils. So to make a very long story short, I think in this project, we've got some kind of science discontinuity. And these people also mentioned that if we want to really have a good progress in science, you need new tools. And I definitely think that in this project, we've got new tools. MRI is not new, but it doesn't have 100 years either. And the new generation coils, I think they are part of the new tools we can use to make the project very new and the result very original. So these people, these philosophers, were talking about science discontinuity and new tools, and they didn't talk about another point which I feel is one of the most important in the project, is the people. I think that if you want to have an interesting project, a project will give some interesting results, you need to have enthusiastic people with you in the project. And I think that all the people I've met so far, either from ITMO University or from Almazov Centre, they are very enthusiastic people who really want to do this connection between physics, MRI, and clinical application. And I think we have gathered in this project all the ingredients to have a very successful project. And as a matter of an example, I would like to give you the summary of a story which can be the story of our project. With this work coming from ITMO University, and a very nice work provided by Alena Shchelokova about this very interesting new generation coil. It's not really a coil in a common way, but it's a wireless coil. And so they did this coil to do imaging of wrist. And they mentioned that the SNR of the corresponding images were very much higher than with the conventional coil. So this will be related to new tools. And then a few years later, one of the PhD students of ITMO University, Ekaterina Brui, did this very nice work about using the images with this coil in order to do a segmentation of the wrist cartilage. So for those of you who are not familiar with the cartilage of wrist, this is something which is very difficult to segment, because it's very complicated, it's very thin, So it's not so easy to do it. So Ekaterina did this very nice work, which has been part of the cover of this journal, NMR in Biomedicine. So which means that people from the scientific field recognize this work as a very new one. And I think this was possible thanks to the combination between the capacity of having a new generation coil and the capacity of generating a new way of processing the images. So we are here now, but we are expecting to have some new results with this, because Ekaterina is working on using this combination of coil in order to modify the acquisition scheme to introduce some new generation pulses in order to be able to improve not only the signal to noise ratio of the images, but also the number of slices we can do in a sequence, and the resolution of the images, etc. So I think this is a very nice example of what this project can provide. And I hope for all the topics we are targeting, we will be able to do this kind of work and to produce the same quality of results. So I would like to end the talk with this final slide about the people, because as I mentioned, the people are central for the success of a project. So we are, as I said, a group of very enthusiastic people coming from different fields, and this is very important for the success of the project. And before wrapping this presentation up, I would like to mention the name of one of my colleagues without whom this wouldn't have been possible. You know, a few years ago, I met my colleague from Fresnes Institute, David Bendahan, who introduced me to the world of M-Cube. And I really want to thank him very much, because without him, I wouldn't be here today. And I'm very proud and honored to be the leader scientist of this project. I hope everything will go well to have a success with this project and very nice results. And Reda, thank you very much for introducing me to these very nice people. So thank you very much for listening to me. I hope we'll have a very nice exchange today. Of course, we would have liked to be all together in the same place. Now it's not possible, but I think it will be possible in the next few months. And we should repeat this meeting. It will be kickoff number 2, but at that time we will be all together. But for now, we need to do it remotely. But I hope it will allow us to still have fruitful exchanges between all of us, and that we are now starting something which will end up with a very nice story. Thank you very much again for your attention, and I leave you with my final slide about the program of today. Thank you very much.
Thank you, David. So, colleagues, do we have any questions?
Just from the chat.
Yes. I try to check chat, but
Okay.
yes, Yasha, please.
Yeah. Hello, David.
Hello.
This is Alexei. So very glad to see you remotely. Hopefully, we will see each other soon in person.
Yes.
Thank you very much for this great introduction of this very new and impressive project. So my question is the following. So basically, you partially answered on it, but I would like to raise it again here. So what is, let's say, from your opinion as a leading scientist, what would be the major result of this project? So in, let's say, 4 years, when this project will, let's say, finished, what we will have? So at least what you want to see as a result of this activity.
My feeling is that we need to, I will see two different parts. The first one will be to have, as I said, new acquisition schemes and new post-processing tools in order to target the clinical problems, clinical issues. But they will be only the first part of it. And the second part will be to really translate this into the clinical world in order to really have the clinician using these new ways of doing MRI on the daily basis, actually. Because, you know, so far, when you look at the different projects, MRI projects, using this kind of technique, you know, it gives you one paper, two papers, and then you never see really clinical applications. When I mean clinical application, I mean using it for the patients every day. So if we are able to design new ways of doing MRI and to translate them into the clinical world, I would consider that the project is a success.
This is a great goal, and I'm very much hope that this will be happening in this project. At least as you have shown, a lot of people from clinical side, a lot of colleagues from Almazova Centre is involved. So we have great chances for success. Thank you.
Yeah, I hope so as well.
Thank you, Yasha. Thank you, David. So I think we have a time for maybe one more question. Is there
Maybe from chat.
Yeah, maybe I'm in chat. Okay, I can check. But it's nothing in the chat. Okay, maybe if there are no questions, still you will have a possibility to ask them within the roundtable. Let's continue. So, David, may I ask you to stop your presentation?
Yeah, I'm trying to find
the green button. You need the same button with the
yeah, but I need to go back to Zoom. Oh yeah,
yes.
It's here. Here it is. Okay. 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 Oh yeah. Okay.
Okay. Okay. Thank you, David. So the next presentation actually will be given by me. For those who do not know me, I am currently hold a postdoc position within the Department of Physics and Engineering in ITMO University. And actually my principal research interests are in applied electromagnetic with particular focus on the development metamaterial-based and hypermaturity dielectric-based devices with, of course, application for magnetic resonance imaging. And within the current project, I will supervise the part related to the this novel RF devices, which David actually mentioned during his talk. So let me now share the screen. Okay, so hope it works. So yeah, today I will give you just maybe more details about our background, which David already mentioned, related to the metamaterial-inspired and ceramic-based devices for clinical MRI applications. And also I will try to give some ideas how we can use these devices within the current project. So usually if we are talking about the clinical MRI, The main tasks here are increase signal-to-noise ratio and resolution. And actually, this problem, of course, can be solved if we will go from the 1.5T to 3T and to 7T. But when we increase the static magnetic field, we are stuck with another problems, such as specific absorption ratio or RF safety, and also inhomogeneity in the some areas. For example, here you can see the abdomen images, and when we make these images at 3T or 7T scanners, we see some inhomogeneous area within the abdomen, especially in the liver. So the possible solutions for this could be the usage of some artificial structures based on metamaterials or ceramic with a very high permittivity without increasing the static magnetic field. And usually conventional setup of clinical MRI includes the large body coil and different dedicated cable connected coils, which is located in the imaged area. So our idea was to use kind of alternative approach when we use so-called wireless coils inductively coupled to this large body coil. And by this coupling, it is possible to focus magnetic flux exactly in the area of interest, thus improving the transmit efficiency and receive performance of the body coil. So one of our first works related to such coils was done in the collaboration with Almazov Centre, where we propose the volumetric wireless coil for clinical wrist imaging. So here you may see the prototype of this metamaterial-based coil. And if you look more deeply, so it consists from a very simple elements. So it was assembled using the telescopic glass tubes and just two PCB boards with copper strips. So, within the body coil, it could be positioned by two ways to scan the wrist image. So one of the position, it is with the hand placed on top of the abdomen, and another one, so-called Superman position. Of course, one of the steps in development of the coils is the electromagnetic simulation of its characteristics. So within this study, we usually check the transmit efficiency, so-called V1+, and specific absorption ratio, what's mean we check just the RF safety. I will repeat again that for this structure, you may see that RF magnetic field localizes directly in the imaged area in the wrist, and it has pretty homogeneous distribution. Regarding the RF safety, so we calculate such a coefficient. It's the transmit efficiency per square root of maximum local SAR, and for our coil is 2 times higher than for the body coil used alone. That actually means that for this with this coil, we may use the RF pulses with the higher amplitude, and also this may be very important issue when we will transfer our technology from 1.5T to 3T, where SAR aspects may be more critical. Of course, we test this coil in vivo with a healthy volunteer, and we compared its perceived performance with the local 4-channel flex coil. So we did a lot of scans. Here just one of the examples for different pulse sequences, which is mainly used in MRI. So as you may see, the image quality in terms of SNR and resolution is quite comparable, but our coil, in comparison with this receive-only coil, has several benefits. Of course, first one is the absence of any cables and electronics. It has very little weight, so and it's of course cheaper than the standard state-of-the-art coil. Also, we can position it with different ways onto the patient table, and it allows us to improve radio frequency safety. So another approach that can be used to localize magnetic flux in some target area is implementation of so-called dielectric resonators. So they work on the same way. So it's just a resonance structure which is operate at the lambda frequency, and it can focus magnetic field in the hollow bore, and also possibly coupled with the body coil. And here is two examples of such resonators for ultra high field MRI. So one of the examples is the water-based resonator 470. This work was done by the group of Professor Andrew Webb. So they developed such a cylindrical resonator filled with distilled water to image the wrist at 70. And another work, kind of a recent one, which was done actually in ITMO University with collaboration with colleagues from France. It was a ceramic probe for MR microscopy with the ultra high dielectric permittivity, which in comparison with some reference coil can substantially improve the image quality both in terms of SNR and the resolution. However, to use such structures at clinical fields, of course, we need to increase the electric constant. And what we recently proposed, we proposed to use the ceramic resonators for targeted breast MRI. So this coil looks very simple. It was just a set of the ceramic rings with the permittivity of 1000 and low loss. And actually, we obtained quite promising results. So again, you may see here that all the signal localized directly in the area of interest. And we made a comparison with the 4-channel flexible coil that demonstrates that our approach can improve SNR by 70%. And also in terms of RF safety, we can substantially reduce the input power that makes the procedure safer. Also, here we did a step toward and did comparison with the state-of-the-art 16-channel breast coil. So, and perform it with the different volunteers, so with volunteers of different BMIs. Also, as summarized in this table, our coil have shown the stability for the different volunteers. So we see that the SNR is quite comparable for all data set with the breast coil. And at the same time, we substantially can reduce the input voltage amplitude. That means this is just the amplitude of RF pulse. So the ceramic-based resonators can be efficiently applied for targeted breast MRI or for targeted MRI of other areas. They also help us to improve RF safety and can be used for highly specialized MRI tasks. And what is also important point here that such structures as dielectric resonators or metamaterial-based coils they applicable to any clinical scanners because they do not require any connection via RF cable. Another issue which happens when we go from 1.5T to 3T is B1 homogeneity, which is associated with such a cold electric artifact, which is actually physically happened due to the changes of the wavelengths inside the body. So here you may see the example of such artifact at 3T and 7T. And to solve this problem, also the group from Leiden University and other colleagues, they proposed to use the high permittivity dielectric pads. So this is just a simple pad which is made from cohesion of calcium, barium titanate plus heavy water. This approach, so it was very well studied for now in literature, but as I know, still did not find application in real clinical practice. But so the studies which were performed, they show very promising result that with a dielectric pad placed on top of the body, we can substantially improve the homogeneity in the liver area, as you may see here. Also, these pads could be very useful for cardiac imaging. And here one of the example how it works. So here we see the two images of the heart with no pad and with pad. And so according to this graph, so it's just a line built within this white dashed line. So we can see that the electric pad could improve the blood myocardium contrast along the interventricular septum. So we also, together with Mikhail Zubkov, did the first studies of these dielectric pads here in St. Petersburg at Almazov Centre. And so our first results demonstrated that really with the addition of such a pad, we can improve visualization of walls of the right ventricle and right atrium. That could be actually very useful for the segmentation tasks. And of course, these structures have several disadvantages. And so the main of them that material parameters can change within the time, because as I mentioned, it's some kind of the cohesion that could degrade. So some materials which this pad contain are bioincompatible. And the main one that this pad are very heavy with a typical weight of 2-4 kilograms, that it's actually not very comfortable for the patient. So recently we decided to solve these issues and to replace the dielectric pads with some ultra-thin compact and flexible structure, so-called metasurface, achieving the same positive effect on the improvement B1 homogeneity. So here you may see one of the examples of this structure. So you see that it's really, really flexible. And the advantages of such metasurface, first, of course, that it's made from non-toxic and cheap materials. It has pretty simple geometry, and its parameters are stable over time, and weight of such a structure is less than 200 grams. So we also performed some in vivo study with a healthy volunteer and compared our approach with the reference case when probably you do not have any either dielectric or metasurface pad, and with the dielectric pad case of the same size. So here you may see that really when we use only the body coil to transmit and on-body receive array, we see some inhomogeneity in the abdomen area, while by adding the electric pad or metasurface, this dark area becomes brighter and image completely changes and become more homogeneous. We plan to use, we plan to continue this study and also to check this approach with the patients. So now just some ideas or the main tasks which we plan to do within the current project. So we plan to develop easy metamaterial-inspired to ceramic-based coil for improvement extremity imaging at 3T, because previously we have coils only for 1.5 Tesla. And as I mentioned, since they demonstrate some improvement of rave safety, it could be very useful at higher fields. Also, we plan to implement the dielectric PETs and ultrasonic metasurface for cardiac and liver imaging and combine it with the quantitative MRI methods, which Misha will mention in his presentation. And the main idea, which actually David already mentioned, that in this project, we plan to make some step forward and to bridge the gap between some theoretical proof of principle studies of these novel devices and directly apply them in real clinical MRI practice and make it helpful for the clinicians and patients. So that's all. Thank you for your attention. If you have any questions, please raise your hand. Yes.
Thank you, Alena. It was an interesting report. Just for me, we're working for a long time together, but still, I'm always in the question because you're having something new every for the period. About this ultra thin metasurface, is it better than the ceramic based coil and the first one metasurfaces with the tubes, or it's better for some particular purpose?
Yeah, if I understood your question right. So look, the metamaterial-inspired resonators and ceramic resonators, it's the resonance structures. So you should tune them to the lambda frequency and they focus magnetic field, and that's why they can improve, let's say, signal-to-noise ratio and resolution, and etc. Regarding the PETs, it has a bit different physical principle. So it's introduced the secondary field, which interact with the B1 field of the body coil, and that's why it could be redistributed. So it's kind of, how to say, they help us to bring the additional field and to make the signal in the, for example, abdomen area smoother.
In the local place. Yes,
yeah,
thank you.
It's just completely different devices for different problems.
So for
of course, the electric PETs also will give you some sort of SNR improvement, but not a lot. So the mainly it works for the one routine.
And will we be able to combine them together, or is it impossible in the future?
I think it's possible, but we need to find the reason why we need to combine them.
To achieve all the purposes they serve in the one place.
But actually resonators, they also help you to redistribute field, right? And to make it maybe also homogeneous in some sort, in some area.
But in some cases, I believe it can be. Let's say when you can have, let's say, resonant metasurface on top and let's say like PET on the bottom.
Yes,
that way.
that's possible. But pets also usually use in the, how to say, in pair, right? So you place one pet on the abdomen and another pet on the back side.
Yeah, on the back side. Thank you.
Can I ask? Yeah. I see also David switched on microphone. Probably he has some
David,
question.
do you have a question?
Yeah. I wanted to ask you. You know, I've often heard people doing phosphorus spectroscopy of heart that they were in trouble doing spectroscopy because the pulse power were not powerful enough. Would you think combining the pad with a conventional coil will allow them to improve this kind of spectroscopy in the heart?
We need to think about it. Probably it could be possible because the pads easily can be used with some local coils. And for the heart, it's really demonstrate the good effect on this spectroscopy. So because in the heart, we do not have so pronounced V1 homogeneity, but so still we need to improve the signal in this area. We can think about it. Also, maybe we can think about some, I don't know, the local coil for the phosphorus spectroscopy, for example. I mean, the local coil based on some ceramic or metamaterials.
Yeah, I think it will be interesting because phosphorus spectroscopy of heart is really an issue for these people.
So I see several questions in the. Okay, one question.
Dmitry.
Yes, I see a question from Dmitry Kuprianov. So last year, the magnet bore diameter increased from 60 to 70 centimeters. Have you detected any significant difference using wireless coil? In 70, we see 60 centimeters. Yes, actually, Dmitry, thank you for this question. It's very important. So for the electric pads, it shouldn't be any difference because, as I mentioned, so it's not resonant and operate on a bit different principle, and within the 60 or 70 centimeter bore, we still will have some secondary magnetic field. But regarding to the resonators, the bore may play actually a crucial role because our resonance structures inductively couples to the body coil, and it means that for 60 centimeters bore, this coupling could be larger. So that may increase. So in this case, we should be very careful because it's so there is a possibility that in this case we will have a bit distortion in the field, I would say like that. But for 70 centimeters, it would work perfectly because the main of our works that we did within the scanners of 70 centimeter bore. I hope I answered. If not, you can ask some additional questions. Okay, and I have a question from Stanislas. Can you comment on the reference voltage when you're using PET for the heart? Do you have in vivo experiment with multiple volunteers? When we use a PET, since it's I will now a bit review the papers of the Professor Andrew Webb group. So when they use a PET and they really checked it with the multiple volunteers, since they locally increase transmit efficiency, they recommend to make a local calibration of the reference voltage, let's say. Regarding to the metamaterial PET, it should work the same way because it also will enhance the transmit field. but still we did experiment only once. I checked several volunteers, but for all of them, there was the same effect.
I can probably add to that.
Yes.
I just remember the numbers I looked up last time we scanned people, and I think we've seen some like 20% increase, 20% decrease in the reference voltage.
Yes, but the scanner, as I know, calibrated easily.
Yeah, but it's not like a local calibration.
Yeah, that's how it was written in Andrew's paper, that they just recommend to do this. This is for 3T, because for 1.5T, we do not have such distortion in the field. Okay. So I suggest to move on. And if you have any other question, please write them in the chat. So Katya, are you here?
Yes, I am.
Okay, perfect. So then first I will do like that. And let me introduce the next speaker, Ekaterina Brui. She is the 4th year PhD student within the Department of Physics and Engineering. She has a background in NMR physics, and within her PhD studies, she has taken a part in the development of MR image acquisition and post-processing methods involving metamaterial-based and deep learning approaches. Within the current project, she will be principal investigator in the implementing artificial intelligence-based post-processing methods in clinical practice. Katya, you're welcome.
Yes, thank you. 1 second.
Yeah, we need the full screen.
Yes, I know. And I would like to switch on my video. Okay, so now I think you can even see me. Probably.
We can see you.
Okay, great. Alena, thank you very much for this introduction. Today, I will tell you about and I will tell about what we are going to do within the project. And all of us know that artificial intelligence is now everywhere, and this approach is they're witnessing tremendous attention nowadays. And what is this artificial intelligence and all these things? Actually, we can tell the artificial intelligence any algorithm which mimics the intelligence of a human, even some number of if and then cycles. And the machine learning is a subset of methods within the artificial intelligence, which traditionally machine learning are trained to perform useful tasks based on manually designed features. So someone has to design some features and then train them, and this way allows to extract some features from the raw data and train them automatically. And a smaller subset of machine learning approaches, the deep learning, is deep learning, and where computers learn useful features and representations of data automatically, skipping this manual step. And of course, nowadays, all these approaches of machine learning, they are surrounding us everywhere in our everyday life. And for the healthcare, for medical images, these methods are of particular interest, taking into account that the healthcare generates enormous amount of very valuable and signals and informations and images. So medical imaging needs these approaches very much, and nowadays they are developing very fast. And the main I think in medical images, the main interest in is focused on such a subset of deep learning approaches as convolutional neural networks. And the main common characteristics of them is that they allow to train features and in parallel, a lot of different features in parallel. And they allow to reduce the size of the data without losing these features, without losing the very important information. So, and a very important thing is that the use of CNN is now available for everyone, not only for programmers, and CNNs become routine tools, as there are plenty of CNN libraries, open source, and tools for their adjusting for a particular task and for their training. So there are various applications of CNNs in MRI, starting from very beginning of data acquisition and involving all steps of data post-processing and even interpretation. So they can be used for image reconstruction, for extraction of quantitative parameters, such, for example, in deep learning-based fingerprinting techniques, for image restoration, denoising, and artifact detection, and for creation of super resolution images, for synthesis images for different purposes, for example, for training a different neural network. They are very frequently used for image segmentation and tissue classification. And finally, they can be used for diagnosis and prediction of outcome. So one of the main benefits of all these approaches is that they allow to extract the hidden information, which is not always, not usually obvious for a human eye, or which can be extremely tedious to extract manually. That is why these techniques may provide neuroradiological markers, both quantitative and qualitative. And within our project, we are working on creation and validation of new MR-based markers, and one of these markers can be markers for cartilage loss detection in different arthritis disease, like osteoarthritis, psoriatic arthritis, or rheumatoid arthritis, or post-traumatic arthritis. Different kind of disease which result in a degradation of cartilage. Oh, sorry. And for big joints, such as a knee joint, which has a relatively simple anatomy, such morphometric metrics are really used in a real clinical practice, and they are proved to correlate with the stages of this disease, stages of cartilage loss. clinically proved, and are used for grading cartilage loss. And such measurements are always based on a cartilage segmentation from the image and from MR image. And the manual method is considered as a ground truth, and it's quite reliable with the reproducibility of segmentation in terms of dissimilarity coefficient, which is indicated here, of 0.88. So this is what a human can achieve in a segmentation of knee cartilage, and the number which is considered as a satisfactory. And as the knee has a relatively simple anatomy, there are plenty of automatic methods, and the methods based on CNNs, they allow to achieve this dice coefficient even higher than a human observer. So the latest approaches, they allow to achieve even higher. And the important thing is that during the last years, the huge databases of marked labeled knee images were created. So this allowed to create these deep learning methods, because deep learning methods need a large number of manually labeled training data. And in contrast to knees, manual segmentation of wrist joint is much harder because of its more complex anatomy. And there are no available data sets, and there are no automatic methods for cartilage segmentation. That is why the metrics which have been proposed to grade the cartilage loss in wrists, they have not been clinically validated, and they were not tested in clinical trials. So we do not know for sure that these metrics can correlate with the grades of cartilage loss. And this metric, they also can be one of the metric proposed was a cartilage cross-sectional area on a particular slice, coronal slice of wrists. And of course, as in a knee joint, the cartilage volume can be considered as such metric. In our project, we intend to investigate, to create first step, to create a tool, automatic tool, to extract the cartilage tissue from MR images, and to investigate if these parameters can be a measure for cartilage loss in wrist joints. So first of all, we have started from creation of a data set. As I have said, that there was no data set existing of manually labeled images. We used the VIBE, 3D VIBE pulse sequence, and we had scanned 11 subjects in 1.5T scanner using standard coil and the coil which Alena had presented. And we had a radiologist who bravely labeled a lot of images. So we had 10 3D images for training and 10 3D images for testing our neural network. So this resulted in approximately 560 images, which were manually labeled by our radiologist. So we used 20 medial coronal slices as in this work to compare with the manual method. So first of all, we have started from creation of a simple convolutional neural network because we had not so much data, and we started with a patch-based training approach, which allows to train the neural network not on all image, but on patches surrounding the pixels which are needed to be classified. So we have adjusted the number of layers, the filters, the number of filters, the size of filters, the number of filters, and many other more thin parameters, which usually have to be adjusted while developing neural network. We did it in a grid search, so we have tested different parameters. So the final architecture looked like this. What we got was that we had a strong correlation between this dice coefficient between the mask, cartilage masks that the neural network got and the manually labeled mask. So we got a strong correlation between the number of cartilage pixels in a slice. So this red-orange curve represents the number of cartilage pixels in the slice, and this this blue line corresponds to number to the dice coefficients on the layer. So here is some example of cartilage segmentation with our neural network. For the medial slices, we got quite a nice result. So around 0.8, it was close to the human observer, which a human observer could achieve. But the dice dropped significantly on the lateral layers. So we decided to use another approach, very well-known architecture of a neural network, the UNet architecture. We adjusted some parameters here. Also in a grid search, we added noise level and batch normalization level. Noise and dropout level in order to make sure that our neural network will not be too much generalized. And so what we got, our dice coefficient on the lateral layers raised significantly, and then we tried to adjust this architecture in order to reduce the number of training parameters and reduce the training time. So we have truncated the last levels, so the deepest levels. This allowed us to boost the training and the time of CNN performance. So we got approximately the same distribution of dice coefficient. And this is only one example. I didn't say this is only one example, just to illustrate. And then we needed to somehow statistically compare these approaches in a group of subjects involved in a testing data set. So, but all hands are different. They have different size, and we couldn't do the layer-to-layer analysis. So we decided to divide the wrist to some zones. The first zone didn't contain any cartilage. The second zone contained cartilage from 1 to 33% of the maximum number of pixels. The third zone contained from 34 to 66, and the fourth zone contained from 67 to 100% of cartilage pixels in the zone. So they are symmetrically located in the wrist. And we got, for this analysis, we got that these UNet approaches allowed us to significantly improve the cartilage segmentation accuracy in the lateral slices. There was a improvement for all kinds of slices, but the main improvement was for lateral slices. So this made this segmentation more homogeneous through the across the wrist. And these are some final results for this for these three neural networks: batch-based, classical UNet, and truncated UNet. So we got the 3D dice. Oh, I'm sorry. It's this one corresponds to 3D dice, and this one corresponds to the medial coronal slices. I'm sorry, this is an error here. So yes, we got the best dice, best performance in terms of dice and in terms of time of training and time of performing for the truncated UNet. And if we compare with manual method, we have performed the inter-observer and intra-observer manual study, and we got that this number is really quite close to what the human observer can do. These are numbers for 2 observers who segment one after another, and this number is for 1 observer who segments in 2 sessions. So, and of course, you can see that the time of performance is 6,000 times less for this truncated UNet. So to conclude for this, I can say preliminary part of the work, I want to say that we have shown that the CNN-based approach is feasible for cartilage wrist segmentation, and now the segmentation of cross-section on medial slices to get the cross-sectional area to measure it, they have the comparable accuracy with human observers. That is really makes these metrics probably useful for to replace a human at this point. So, but of course, we have a lot of things to do within this project, as we did not succeed in creation of in segmentation of 3D volume, and still these numbers for 3D dice are not very high. So we have to increase the accuracy of 3D segmentation by different approaches, and first of all, by, of course, by extending our training sample, including the patient's data and so on, and then to use some other approaches which will allow us to get different features different from we got here. For example, we can use 3D CNNs in order to use 3D features of cartilage, which are really different from other tissues. We can use transfer learning. We can learn. We can train our network on open source images. We can use some advanced techniques like attention technique and etc. And the second task for our project is to classify the small joints in the wrist joint, as this joint consists of a large number of joints. And sometimes, for example, osteoarthritis, it affects only 1 or 2 joints within all the wrist. And the last but not the least, and not the easiest step, and maybe probably is the most hard step, is to validate these metrics, the cartilage cross-section area and cartilage volume in clinical trials. So thank you very much for your attention. And I will be happy to answer questions.
You, Katya. Codex, do we have any questions? Katya, maybe I have a small question. Yeah, you mentioned in the beginning that actually this deep learning approach was well studied for the knee cartilage, if I understood correctly. But what do you think, in your opinion, if, for example, we will somehow, I don't know, develop some new very cool coil and will substantially improve the knee image? Would it be still interesting for scientific community if we will, also combine this RF approach and artificial intelligence approach for the knee imaging? Or it's very, very well studied?
No, it's well studied, but you know that the resolution of images usually is always very, very important, because the precision of cartilage volume or cross-sectional area measurement depends very much on the resolution of the image. So always some very precise measurement need high resolution. So if it will be possible to increase the resolution in any place of the body, this can contribute to the quantitative and morphometric measurements.
Okay. And I see the question in the chat from Dmitry Kupriyanov. Is the cartilage segmentation to the image contrast like DRE plus fast iteration? Can we train algorithm for quantitative MRI like 2T maps or T1?
Yes, of course. Thank you very much. Yes, that's gradient echo with fat saturation. That's true, 3D gradient echo. And yes, we can train this algorithm for quantitative MRI. We are going to use this technique in T2 mapping of cartilage, because we can use our data set for pre-train the network and then to train it on new images, T2 weight, not T2 weighted, but T2 maps to extract T2 max of cartilage in wrists, of course. Yeah. Connected.
I think it's just the part of the previous message.
Oh, okay.
Okay.
Yes, and the very important thing is that, yes, David have written that we can think about combining multiple images to train the network. That's one point, and it is really important for the routine practice when you need to use different pulse sequences, and this is the first thing to do. And the second thing to do is, of course, to train our networks on a multi-institutional data sets coming from other institutions and segmented by our other specialists, because now we can only say that this technique can reproduce the approach which our radiologists apply, but I think that it will be very important to train on images acquired with different approaches.
Okay, thank you, Katya. Since we are out of time for more than 30 minutes, I suggest maybe to move on. So, and the next talk will be given by Dr. Mikhail Zubkov, who is assistant professor of the Department of Physics and Engineering at ITMO University. And his work mainly focuses on pulse sequence development and optimization, emphasizing quantitative imaging, data processing, and their clinical applications. And Mikhail, within the current project, will supervise this direction. Welcome, Misha.
Okay, so good day, everyone. So I think many have already mentioned the problems and the possibilities that the problems that are present before this project, and the possibilities that our developments and the possibilities that are opened due to the developments that have been made here. So I'm going to be talking today about how we can apply those possibilities in the development of the radio frequency devices in quantitative methods in MRI. So I'm going to review a few of the methods that allow quantitative MRI, and I will point out some specific downsides, or maybe some specific points in these methods where our RF device developments can be applied. And I will focus primarily on quantitative imaging in liver, but these methods can be, in most parts, extended to imaging of heart, muscle, and joints. So with quantitative MRI, I would first point out what techniques can be used for relaxation, then move on to magnetization transfer, diffusion, and mention also perfusion. I wouldn't mention things like quantitative susceptibility mapping, because I think there would be some other reports on that later on today. So with relaxation, we usually look at T1, T2, and T2 star relaxation. There is also T1 raw relaxation, the relaxation in the rotating frame, but I won't be also discussing that today. So with T1 relaxation, we usually have three or four methods for measuring it. It's the inversion recovery. It's considered the gold standard for measuring T1, but it's quite slow because it requires repeating the experiments with different inversion time. There is a promising techniques under the names Molly and Sasha, which are fast, which can acquire the relaxation curve just in one or two excitations, but they're significantly affected by B1 inhomogeneities, and usually require the knowledge of the B1 distribution to apply them correctly. And the difference between Molly and Sasha is just that one uses inversion and the other one uses duration. And the third technique used for T1 mapping is very well flip angle technique, and that just consists of two imaging sequences with different flip angles, and then deducing the relaxation time via some some simple mathematical procedures. And these are also affected by B1 homogeneities because you require the exact knowledge of your flip angle throughout the whole image. So with the T2 relaxation mappings, the common and sort of standard way of measuring T2 relaxation is CPNG sequence, which is just a multi-echo sequence with different images, but it is also affected by B1 inhomogeneity because it leads to stimulated echo formation, and it's a high specific absorption rate sequence. So its usage, particularly in 3T, is rather limited. And another T2 relaxation technique is the variable Philipp-Engel technique, but it, despite being fast, it also requires good knowledge of B1 and B0, and also additional measurements of T1 relaxation to deduce T2 relaxation then. And T2 star relaxation is measured by multiple gradient echo technique, also used for quantitative susceptibility matching, and it affected particularly in QSM by a lot of things like flow, fluid homogeneity, chemical shift, and eddy currents, but some of those could be either mitigated or reduced. So what do we do with those mappings? With these mappings, you can do just direct measurements of mapping, and it was shown that, like for T2 relaxation, that T2 correlates with the fibrosis stage and also correlates with the serum biochemical liver markers, liver damage markers. So we can just use the direct T2 measurements and improving those T2 measurements, say by improving better, by introducing better refocusing or better field homogeneity into the imaging. We can improve the, say, the error. We can reduce the error in the T2 measurements. Then I would probably mention the fact that the relaxation measurements don't really reflect the actual relaxation and the actual quantitative properties of the tissue, because on subvoxel scale, we can have subvoxel averaging due to the different tissues present in the voxel, or we can have different compartments even in the same tissue, and the exchange between these compartments can influence the value of the parameters that we measure. And that also can be used to introduce some kind of biomarkers, and that would be kind of a success. And I would now present kind of a success story, which where such a combination of biomarkers was introduced into clinical practice, and that relates to the T1 measurements. And first, it started as a multi-compartment model for fibrosis modeling, and people just modeled the fibrosis as some change in a parameter which relates to interstitial fluid contents, and that combined that into the specific software package which was introduced into the clinical practice. And first they shown that well, T1 G2 star mappings can provide some additional parameter called the corrected T1 measurement, and that is indicative of fibrosis. And then they performed a large scale clinical investigation, which showed that actually that combined T1 and just common T1 can be related to event-free survival rate of the patients with liver fibrosis. So another thing that can be done with T1 and T2 star mapping is measuring perfusion, but that is done in a very particular protocol which was introduced just recently. And in that protocol, you would ask a patient to drink some water and then image the patient for quite a long time, like an hour, constantly repeating T1 and T2 measurements, and then the modeling can be done of the water input, water intake by different organs, say by liver, and the reference intake by muscle, and then the delay in the water arrival into the liver can be indicative of the perfusion deficits in the liver. So that is the things that can be that are the promising techniques in relaxation measurements. Another thing that can be used for fibrosis staging is magnetization transfer. And magnetization transfer, particularly macromolecular proton fraction imaging, was introduced around 10 years ago, and now is a promising technique for imaging macromolecules, first in the brain, and then also there is an application of it to the liver. And it was shown that an increased fraction of macromolecules correlates with fibrosis. But the problem with liver imaging with macromolecular proton fraction technique is that it's very SAR demanding technique, and the efficiency of it is not very high when doing body imaging, and thus increasing the B1 field homogeneity and reducing the SAR load, which was discussed previously in a few talks. So could be a promising extension of the MTF technique into the liver imaging for fibrosis. Finally, another quantitative parameter can be derived with a different technique, and it's diffusion coefficients, and these are usually measured by EPI pulse sequences in head and body. Depending on the strategy that you use for diffusion imaging, you can measure a number of parameters like upper diffusion coefficient, ADC, or you can measure a number of parameters with related to perfusion using the intravoxel incoherent motion technique. Also, there is a extension to non-Gaussian diffusion, which can be in the second say approximation represented by kurtosis measurements. So these have been studied for a bit in the connection to the liver fibrosis, and it was shown that that ADC is decreased in the with the increases of fibrosis stage. Also, if IVIM is studied, the perfusion was shown to decrease in the fibrotic nodes, and it was first shown in animals and of course then shown in humans. But later also it was shown that kurtosis is not indicative of fibrosis, so it wasn't really, it's not really a method that can be used for fibrosis analysis. So with that, I think we can point out a number of directions that can be used in our work package or in our project with regards to quantitative imaging in liver. So we can probably correlate the diffusion-derived perfusion changes measured with IVIM with relaxation-derived perfusion measurements measured by time-resolved relaxation mapping. Also, there is a possibility to improve the multiple models based on the perfusion measurements. Also, there is a possibility to apply the pads and the ceramic pads and the metamaterial pads to improve the macromolecular proton fraction technique because they provide, as we discussed before, better SAR efficiency and better RF homogeneity, and that can also lead to an improvement in general of T1 and T2 mapping sequences for liver imaging. So with that, I would like to thank you for your attention and probably wait for some questions if we have time.
Thank you, Misha. I think we have a time maybe for 1 or 2 questions. Yes, Josh.
Thank you, Misha. I have like probably a naive question, but are there any new special techniques that you can win from B1 inhomogeneity? So if you can create, let's say, some device which will destroy the homogeneity, but for some reason, for some, I don't know, pulse or whatever, it will give you some benefits from this.
If maybe I can only suggest, if you would know the exact inhomogeneity that you create, maybe you can just introduce that into the analysis of your relaxation times, and with that you would sort of reduce the need in imaging the actual B1 distribution in the body. But that is a very sort of slippery way, because the B1 inhomogeneity would be different for every person, and you wouldn't really know which one you would get. But generally, people try to use homogeneity.
Sure. But like, probably there can be something
with the inhomogeneity, the only thing you can do, I think, is introduce some kind of parallel imaging, because inhomogeneity is related to parallel imaging and like different sensitivity profiles. So we have a comment from Dmitry Yanov that it's very interesting to test metamaterials homogeneity correction for QSM. Yes, for QSM, I think today we have a talk about that, and maybe we would get more information on QSM later on today.
Thank you, Misha. Once again, colleagues, I suggest maybe to stop here and to make a coffee break, and back to our meeting at 12:00. So we still have 4 more talks. 2 of them will be given by our colleagues from Almazov Centre, Professor Vladimir Fokin and Professor Olga Moiseeva, and another one by the colleagues from CRMBM, Joris Fournel and Stanislas Rapacchi. So let's meet here in Zoom in 15 minutes.
12.
So, dear colleagues, it seems we are ready to start the second part of our meeting. So, and first let me help the speaker to share screen. So our first presentation will be given by Professor Vladimir Fokin, the head of the research laboratory of magnetic resonance imaging at Almazov Centre and the leading Russian specialist in MRI diagnostics. His main directions in scientific and clinical activities devoted to improving radiology, developing and introducing into practice new promising diagnostic methods of MRI in neuroradiology. Vladimir will mentor all MRI experiments and participate directly in experiments with humans in the current project framework. Vladimir, you're welcome.
Hello, everyone. Thank you, Alena, for kind introduction. My talk was a goal to switch your physical point of view to radiologist point of view, because I'm radiologist. And if you look at heart, it's very difficult for understanding without sign and anything, but you can see very bright area in the left ventricle, it's situation after coronary artery disease, after infarct. You see total almost for a whole thickness of left ventricle, it's scar. We using usually late gadolinium enhancement after injection, gadolinium contrast media with delay 5 or 10 seconds. We you choose TI's count to 0 signal from normal myocardium. After that, you see clear the scar after infarct and cardiovascular. In another case, you can see more difficult to differentiate using more frequently used phase inversion recovery pulse sequence. You can see you see subtle, you see arrow and one subtle bright areas on the left ventricle. Next case. Next case, it's more difficult, one more than the more difficult to differentiate. It's really main problem. It's scar affect only subendocardial area of left ventricle, and we need to increase space resolution. We need to decrease our slice distance to well visualize this data. And case of inflammation, for example, myocarditis, you can see here, we are using 2 pulse signals, usually on the right hand, it's myocardial edema with tuned inversion recovery, T2 star, and you see bright area of edema of myocardium, and also using a pulse phase sensitive inversion recovery to see accumulation of the gadolinium contrast media. And last one about myocarditis, you see the so-called echo chamber. It's left ventricle, right atrium, and left atrium. You see small white dots in myocardium wall, as well and right side. The promising tools from our from radiologist point of view, it's also a quantitative data for using T1 mapping, especially because T1 can help us to differentiate normal myocardium, diffuse fibrosis, and we can correlate data of late gadolinium constant imaging and T1 mapping imaging with color mapping. Also, it's very interesting to assess, to obtain some data about intra and extracellular volume to differentiate healthy myositis, and after post-contrast measure and assessment plasma volume in intracapillary can help to differentiate some inflammation process. The main goal from the main demand from radiologists and clinicians is increase the space resolution. For example, you can see intraventricular septum, its thickness more than 5-6 millimeters, but you can see if right the round, you can see it's only 12 pixels. Why? Because usually we use for example, 400 millimeters and image matrix approximately 200 by XL. And it means we have 1 pixel for 2 millimeters. In this case, in left ventricle, it's not problem. But if we discuss with right ventricle, because thickness less than 4 millimeters, usually it gives us only 2 pixels. But main problem happens when we take to see we try to see the right and left atrium because thickness 1 or 2 millimeters, no more. And in case it's healthy myocardium, we see dark areas. In case of edema or fat or scar generation, we see bright areas. It's very, very difficult. It's gives us only 1 pixel. And from our cardiologists, especially for surgical arrhythmologists, we have a clear demand. Please do something to give us not 1 pixel, but at least 2. The better to have 3 pixels because it can help us to calculate area of fibrosis, especially in left ventricle. As a patient with arrhythmia, it's helpful for arrhythmologists to planning and select areas for some interventional procedure. If you look in state-of-art guidelines, European Society of Cardiology for patients with atrial fibrillation, you can see the in the bottom you can see late gadolinium enhancement cardiac magnetic resonance imaging. It play a very small role, but any cardiologist sure that these images can help, and it's very, very clear decision-making imaging for planning surgical procedure. But we have some limitation because, as you see on some papers, it's very, very rarely due to space resolution. And usually from USA, from Utah University, using only statistical probability of fibrosis in the left atrium, no more. And second paper also very interesting to using some quantitative on tissue characterized pulse sequence assessment epicardial for endmark and for inflammation. And it's possible to do not only with CT with low density area, but also it's possible to do with cardiac MR as tissue more sensitive. About liver, pathogenesis is very difficult. I say it about later, but it's 3 main markers, main player in these processes. It's fat accumulation, it's iron accumulation, and also ischemia. This is 2 most player in the formation fibrosis effect of the liver. And our goal to find first early signs on MRI scan of the liver to find reversible changes of the liver. Previous speakers opened many ability to quantification of fat and iron assessment on the liver. It's not only signal intensity rates, it's proton density, fat fraction, it's many methods of relaxometry, T2 and T2 star. More promising is quantitative accessibility mapping, but some papers also using mass spectroscopy with pulse sequence during 1 breath hold. Now, in clinical recommendation for patients, for example, for chronic heart failure, we're using elastography methods. Usually it's ultrasound elastography, but with assessment of rigidity of liver, we can assess fibrosis and clinical advantage for selecting patients for heart transplantation. In our center, usually we working with T2 star mapping. It's method for assessment of iron overload, for sickle cell anemia and another hematologic problem. It's very easy. In red line, you see typical liver tissue without iron overloads, and after increased iron overload, you see more degree, more curve on the decay on the curve on the graph. We're using 12 echo, and you see how to decrease intensity of the liver. And after calculation, and after you can choose manually area of interest, we can build graphs. And after equation, you can see using, for example, this Excel tables, you can calculate liver iron concentration depending of R2 star and T2 star in milliseconds. These methods well correlate with liver concentration. You see some papers in calibration curve and dry concentration in the liver. Also, FDA approved FARIScan technique for assessment of the liver concentration, and see the paper for good correlation between data obtained from T2 star and FARIScan T2 techniques. But we have some problem because liver it's not consist only from iron, only from fat, also another tissue. Iron usually easy visualized. You can see in face, opposite face. On the left hand, you can see decrease of imaging sensitivity from the liver. But in face pulse sequence, you can see evaluate of signal. It means in liver also we have a fat. And main problem, how do differentiate increased level of iron and increased level of fat on this. And if you see on the spleen, you can see any changes in signal intensity. It's help us without calculation or with a visual assessment to suspect the accumulation fat and iron in some situation, for example, for non-alcoholic fatty liver disease. Sorry from slide, but next technique, more interesting and very easy assessment, it's proton density fat fraction. It's easy to calculate like signal intensity from the fat divide from signal intensity water and fat. And main advantages of this is this technique accurately reflect concentration of the fat, especially triglycerides in liver tissue. Next slide about congestive hepatopathy in patients with heart chronic failure. In this case, we increase the pressure of the right ventricles, and it means delay blood in low cavernina and also in the liver. It's helped in several clinical situations like pulmonary artery hypertension, ischemic cardiomyopathy, cerebral some stenosis, and also assessment of some surgical procedure, for example, Fontan procedure for hypoplastic left heart syndrome. And congestive hepatopathy, it's very interesting to visualize in early stage when we have only microbleeds, only sini changes in liver. Congestive hepatopathy, it's also called chronic cardiac hepatopathy, and previous term was cardiac cirrhosis. The outcome for patients with heart failure improved if we can assess early stage and select the patient with cardiac cirrhosis. It will decline for some procedure. Pathophysiology, it's very difficult, but I take attempt on only 2 points of this. It's hemorrhage. You can see red dot in the liver. And after that, we can see fibrosis. This picture, so-called nutmeg liver or muscat liver in Russian language, but you can see accumulation of red cell hemoglobin. It's one of main layer in the formulating of fibrosis. And for selecting the patient in our center before transplantation for the heart, a patient with chronic heart failure, we select the patient using, as I already said, usually elastography, but it's end stage and not fully reversible situation. Our goal is find some data about iron and phosphate statement and select the patient with early stage of nutmeg liver. Some example of MR elastography. You can see on the left side not more changes in signal intensity of the liver, but with assessment of elastography stiffness, you can see red color. It's a high level of stiffness of the liver. It's very, very useful, but it's final stage of fibrosis in the liver. And the last, from our point of view, and Mikhail and David said about the quantitative stability mapping, more promising tools to exclude and separate signal from fat, signal and T2 star effect in the liver, and split or divide data of iron and fat. And our idea and our advantages to improve visualization in the liver, it's with using quantitative methods to find some data about small changes in the liver in congestive hepatopathy. It seems to me, working with ITMO and our colleagues for MRI, we find to improve some pulse sequence using T2 star, T2 mapping, and with QSM and PDFF. But problem as well in heart, we have moving organs, especially in heart, and also and the liver. We must do only 1 or 2 breaths hold, preferably 1, or using or navigating. And because liver is so close to anterior wall of the abdomen, maybe some metamaterial using PET will be useful to assessment more surface located organs. It's my point of view how we help to clinician, to our doctors to select the patient, improve visualization in liver and heart. Thank you for your attention.
Yeah, thank you, Vladimir. I think we have a time maybe for 1, 2 brief questions. Okay. I think we have a comment from David.
Thank you, David. Of course, partial resolution, it will be an option. It's our final goal, maybe concrete goal in our sequence, but textual analysis will be interesting.
Can I also comment on this?
Yes,
So,
no.
thank you very much, Vladimir. Very interesting. Related to spatial resolution, we are kind of restricted by gradient coils, not by metamaterials. So, and 2 millimeter is more or less what we can achieve at.
I don't know what the resolution is limited by. Is it limited by the fact that you have a lot of tissues around it, around heart, and you need to do phase encoding proper phase encoding to put all of the tissues in your image, so there is no aliasing in there, and it takes a lot of time to do that phase encoding? Or is it just that you are limited by the gradient power that you have?
I suppose we limited by gradient power, maybe restriction in the scanner, but I give some information about using some technique like zoom, promoted by Siemens, when we increase the ROI of interest. But I don't clearly understand about matrix, image matrix, because if we decrease the ROI and the same metrics, I suppose we resolve the problem.
Yeah, you probably would resolve the problem, but that requires either higher gradients, and that might be also something.
Could it be just sequence settings?
No, it requires a specific sequence, definitely. Yes. But also there might come up a limitation in gradients and a limitation in SAR. Okay.
But can we, let's say, focus all B1 in the heart, and let's say if you can, that would be nice. If you localize only B1 in the heart, in this sense, this can be the same like a breast. And
yes.
Yeah.
That's true. We have one.
Thank you, Stanislas, for the question. Do you inject patient cardiac lever, and what perfusion imaging acquisition do you perform when injection? Usually in magnetic resonance clinical routine examination, we using multi-dynamic assessment of the signal intensity, and the dynamic phase usually continue 7-10 seconds. And also we do multi-phase CT scanning with contrast media. We don't have any experience about perfusion with high time resolution, 1 or 2 seconds. It's possible, for example, in brain and perfusion imaging.
And one more comment from Dmitry Kundryan.
Dmitry Kundryan comments the slide thickness is the most critical parameter for the fibrosis assessments. We have some experience in pre-ablation studies, and we have to use 3D LGS acquisition. Yes, thank you, Dmitry. Last week we took part in PhD finishing in Medical Military Academy, Sergei, I forgot the name, and for assessment of the left, using 3D LGS acquisition for assessment of the left ventricle. But we discussed after that the problem also for assessment arterial, especially right and left, for pre-surgical planning for ethnologists. It's the same problem, and I suppose maybe advanced with 3D LG acquisition give us some possibility.
Okay, thank you, Vladimir. So, colleagues, let's move on.
Thank you.
So, our next talk, colleagues, could you please keep us silent? Yeah, our next talk will be given by Professor Olga Moiseeva. She's director of the Heart and Vascular Institute and head of the Department of Non-Coronary Heart Disease at the Almazov Centre. Her main scientific interest research related to the study of the pathogenesis of inflammatory heart diseases and cardiomyopathies, pulmonary hypertension, acquired heart defects and aortic pathology, and cardiovascular pathology in pregnant women. Within the current project, Olga will supervise a part related to the advanced heart disorders methods and accompany patient scanning. Olga, you're welcome.
Good morning, everybody. In my report, I will briefly tell about our center, potential areas of MRI study, and data from our previous research. Almazov Centre is the biggest national clinical and research center. Patients from 40 Russian regions can receive specialized medical care in our center. This is almost half of the Russian population. The center have over 1,500 beds and includes main clinical complex, rehabilitation complex, perinatal center, children rehabilitation complex, and Polenov neurosurgical center. We have 7 research institutes and departments such as Biobank, Clinical Trials Unit, Pathology Unit, and certainly Radiology and Nuclear Medicine units. Cardiology and cardiovascular surgery are the key clinical and research areas of our center. Further, I will focus on specific areas that I think will be important for the future MRI studies. The most promising areas are related to the diagnosis of inflammatory heart disease, assessment of the right ventricle structure and function, and diagnosis of myocardial fibrosis and sudden cardiac death risk stratification. Differential diagnosis of myocarditis is one of the important clinical fields in our center. We routinely perform about 100 endomyocardial biopsies annually in patients with new onset heart failure. We use to verify the myocarditis diagnosis, histological and immunohistochemistry analysis data. At the same time, we also perform cardiac MRI in all patients. Previously, we analyzed the distribution of MRI criteria in patients with various morphological forms of lymphocytic myocarditis. Active myocarditis was diagnosed in the presence of cardiomyocyte necrosis in accordance with Dallas criteria. Chronic myocarditis was confirmed in the presence of myocardial fibrosis by muscle staining biopsy samples. As a result, we made the following conclusions. The LTA absence with a high probability excludes myocarditis diagnosis. Myocardial edema combined with EGE and LGE has high sensitivity, specificity, and diagnostic accuracy of the myocarditis diagnosis. The MRI sensitivity in acute myocarditis is higher than in chronic one due to the discrepancy between the fibrosis and edema fields. In chronic inflammation, the LG areas mismatch with myocardial edema, while these fields match by 69% in acute inflammation. Diagnosis accuracy of the MRI protocol decreases in patients with chronic myocardial inflammation. Another area of our interest is pulmonary artery hypertension, a disease with an extremely poor prognosis and a rapid development of right heart failure. Due to the right ventricle anatomy, cardiac MRI is the gold standard for the right ventricle structure and function assessing. PH patient can be used as a perfect subject for these studies. We have all the possibilities because we are one of the biggest Russian centers where PH patients are examined and treated. Here are the data from our registry and the diagnostic tests that we perform PH patients in our center. Analyzing two-dimensional echocardiography, we identify simple parameters which can be used to risk stratification in patients with pulmonary hypertension. We revealed strong correlation between right heart fraction area changes by echo and the right ventricle ejection fraction by MRI. Additionally, MRI allows assessing pulmonary artery morphological changes in PH patients. We revealed that the pulmonary artery distensibility index can be used for evaluating of pulmonary artery remodeling and prognosis of PH patients. Another promising area of MRI study is related to the left ventricle structure and function assessing in patients with hypertrophic cardiomyopathy. Currently, cardiac MRI is widely used for sudden cardiac death risk stratification based on LGE volume assessment. But myocardial fibrosis changes are variable, as you can see from the data of histological examination. Therefore, improving the diagnostic accuracy of cardiac MRI and expanding the post-processing capacity are extremely important. In our center, at least 50 septal myectomies are performed annually. We perform cardiac MRI for all patients before open heart surgery. It seems to me that additional MRI and morphological comparison will be interesting. In conclusion, I would like to highlight what clinicians expect from MRI study. We hope to improve the quality of imaging, the diagnostic accuracy, and to get the opportunity quantitative post-processing assessment. Thank you for your attention.
Thank you, Olga. Have any questions? Okay, I see that we have a question from David in the chat. So congratulations for this very nice talk. I had in mind that T2 mapping could distinguish inflammation T2 increase and fibrosis T2 decrease. Do you have such an experience in heart?
Oh. We don't have some experience to detect interstitial fibrosis in the heart, but I please Vladimir help me for MRI study in the heart.
Yeah, David, we don't have a capability to do T mapping of the heart on both scanner and 1.5 and 3 Tesla, but I hope with help of our colleagues for ITMO, we can do it. And we have only data from the paper, many papers about usefulness of T2 star mapping for differentiate fibrosis on T2 mapping.
We have two more questions. The first one from Dmitry Kiprianov. Is post-COVID complications like myocarditis is different from the MRI pictures of classic myocarditis? We've met with the situation when clinical symptoms are typically myocarditis, but MRI can detect inflammation and fibrosis. According to your experience, is the situation typical for COVID?
It's a very interesting question. We see many patients with heart failure with reduced injection fraction, but this heart failure have different etiology. Hypoxia damage of cardiomyocyte, inflammation, cytokine storm, and cardiomyocyte damage. And when we perform MRI imaging, we see a classic LG and edema features in these patients.
Thank you, Olga. And yeah, another question from Stanislas. Thank you, Olga, for this presentation. Do you record the positions of local LGE? So intramural, endo-API, and anteposterior septal. These features sometimes distinguish subpopulations of cardiac patients.
Thank you very much. In patients with dilated cardiomyopathy, we see intramural LG pattern. In patient with myocarditis, we see sometimes intramural and subepicardial pattern. In patient with hypertrophic cardiomyopathy, we see intramural severe LG pattern, focal LG pattern.
Okay. So thank you, Olga. Yes, colleagues, if you have maybe more questions to Vladimir and Olga, I suggest to leave them for the round table. And now let me introduce the next speaker, Joris Fournel. He's a PhD student in CRMBM, and Joris' main subject is deep learning of medical image segmentation in order to improve cardiovascular risk predictions. Joris, you're welcome.
Yes, hello everyone. I hope you can hear me.
Yes, we can hear you, but we do not see your screen.
Do not.
You should share, yeah.
All right, so I would like to thank you, Alena, for presenting me, and to thank all of you for letting me speak in this conference. I'd like also to especially thank David for inviting me. I'm very honored to speak in front of you, so I will start right now. My presentation is entitled Deep Learning for Cardiac MRI Image Segmentation from Data Acquisition to Segmentation Quality Control. So the presentation is basically from the result of a work I had with people from the hospital of Latimone in Marseille, where we worked on segmentation of the left ventriculum that you can see here a picture, and especially on the segmentation of the trabeculation and the papillary muscles, which was the first time it was done with deep learning techniques. So we were published actually in Radiology recently, and so it was a study made where we had selected 449 subjects that were manually segmented by a trained radiologist. And we started, so on the left, you can see a figure from our paper showing all the different steps we implemented, starting from the MRI acquisition and finishing with the clinical information. And I wanted to illustrate today all the steps that you have in between that you can solve with artificial intelligence. So to say a word about the results we had, to say how powerful AI can be, we focused on the trabeculation segmentation, and in terms of results, we had an average dice of 0.63, can seem small, but it's not small because it's a very hard structure to segment for the AI, and it was higher compared to the human inter-observer, which was 0.44, and it was even higher than the intra-observer, which was 0.58. And we had the same result for the automatic quantification of the trabeculation mass to total myocardium mass ratio. We had higher correlation with 0.92 compared with the intra and inter-observer. So that's just the results in the end we had. But now I want to illustrate all the problems problematic that you have, because when you start with a data acquisition, you have a full volume and you are very far from the final results. So the first thing you might want to do is a slice selection problematic. So when you have, for example, images that you want to keep, as the one on the left, and images you don't want to keep because there is nothing to segment there. You can have the same problem in CT images with lungs, for example. You want to keep the images with the lungs and do not keep the one that do not possess it. This is extracted from a work we did on the COVID lesion after. So you can solve actually pretty easily this problem with a convolutional neural network, especially if you have segmentation of your images. You just need to make two bags of images, one bag where you have the slices that interest you, and the other one with a bag where with the image you are not interested in. And you just train a classifier. So this is a network we use in the paper to classify each slice. It's a very simple convolutional neural network, and that's how we solve it. So it's very simple to implement, and it's an essential step if you want to implement your AI solution in reality in a hospital. So that's a way to do it. There is also other ways to do it. That's from a paper from Comenda et al. On epicardial fat segmentation in CT. And he includes the slice classification task you can see above inside the network used to do the slice segmentation. So that's another way to do it. But still, I wanted to illustrate this application of CNN you can do on slice classification. So that's the first one. The second one is a region of interest detection. You might have an image, but what you're interested in, for example, us, it was the left ventriculum, just a small region in the image is interesting you, and the rest not really, is not bringing anything. It can bring a context, but for this task it's not bringing a lot of context for the trabeculation position. So, and it's taking a lot more memory, and memory can be very quickly a problem with CNNs. So another thing you can do with CNN is just detect the region you're interested in very simply. You don't have to produce any more data. If you have your segmentation from your main data set, you just, as here, you can use, again, a segmentation network, and you take the input image with a large field of view, and you just segment for example, the left ventriculum. For this network, I took the original mask where there was a myocardial, cavity, trabeculation, and papillary muscle classes, and I just converted them all to one class for the heart, and I trained the network to segment that. And then after, I was able to, in inference, to recover the center of mass of the segmented region, and then I can just crop around it, and that's how it's done. That's another thing that's doable. And then, of course, when you have done these first two steps, you can more focus on the segmentation itself. So here you have an illustration of all the the regions we segmented. And for that, there is many solutions. You know, I will not speak about all the networks that exist, UNet, with attention, without attention, SegNet. There is many things that exist. I think the most important thing is not necessarily the architecture. It has its importance, but the most important thing is the quality of the data. You cannot be picky enough about the quality of the segmentation, how you select your patient. I would suggest to focus on that more. So for our paper, we selected, we combine, because in general, it works very well when you combine two different models. We combine a 2D model with a 3D model that you can see under, and our final prediction were mixed between them. And a final thing I want to speak to you about, which I care a lot about, is quality control. Because when you have a segmentation, and especially in clinical application, okay, the software will give a quantification from a segmentation, and the doctor will infer prediction about the state of the diseased person. But how can he know that the segmentation is trustable? And that's a big question, because the model, normal model, they don't tell you how sure they are about what they say. So that's why quality control, especially in medical application, is very important. And we measure in general the quality of a segmentation using the DICE index that I think most of you are familiar with. And so for each class, you can have the number between 0 and 1, and the closer it is to 1, the better it is. And we, in our work, we actually tried to predict those DICEs with a neural network. So it works very simply. You take your segmentation and the image as input, and you train a network to predict the DICE of each class. That's almost as simple as that. And it works quite surprisingly. So I will show you from another paper that is in submission about this technique. With the spreadsheet you see here is the mean absolute error we had on predicting the DICE for each class, for background, left ventricular myocardium, cavity, etc., trabeculation. And so you can see the errors. We implemented two approaches, a 3D and a 2D approach. But the error in both cases are very low. If you consider that the DICE is between 0 and 1, we have error of about 0.02 on the myocardium, on the cavity, on the trabeculation as well. So even for small classes as the trabeculation, we were able to predict if a segmentation was good or was bad. And that's a pretty interesting result. It's not so complicated to put in place, but so I just wanted to share with you this work. So to go back to an overview of what I just presented, in the end, that's how when we integrate all of that, it ends up like that. We have an MRI acquisition in DICOM format, for example, and we apply the first slice selection step. After on those kept images, we detect the left ventriculum, and then after we crop around it, and we can segment it more easily. And then on the last step, we predict the quality of the segmentation we had at the step number 3. And based on a criteria that we decide, okay, if the DICE is smaller than 0.7, I don't take it. You know, based on a criteria, you derive your clinical information, and you can use data. So that's it for my presentation. I have a question. If we have time, I can present to you because I heard that you spoke about the idea of bringing the models into the hospitals, and we actually created two software, one software for this application, and I can show you quickly what it resembles.
Yeah, I think we have a time. Let's have a look. Thank you, Joris.
So we built a software that we gave to Stefan Petersen and Nei Ong in Great Britain, and they applied it on the UK Biobank. And so it's coded in Python, and it takes as input DICOMs. And then after you just launch the segmentation, and you recover all the patients in your database segmented like that. You recover all the quantitative information in one step, saved in CSV files, for example. You also recover, as I showed you, the quality control. You know, you have the dice predicted for each class, and if it's good or bad. And then after, you can, of course, visualize the result. And what is interesting is that also you can detect, for example, in red here, it's a segmentation that was detected as not good. And indeed, it is not so good. And so that's something. And to illustrate what it resembles, okay, that's the segmentation you can have on subjects that were not seen before. So that was used by the English people I spoke to you about. And we did the same thing recently with Smart Lung, with our models to segment the lesion in the COVID. So you take as input CT scans, and after you just launch the AI segmentation, and it segments all the lungs and the different lesions, the consolidation and the ground glass. And then after, you can very easily derive the volumes and the extent of the development of the lesions. And this one, Smart Lung, was installed in the hospital, in the Latimon hospital. And it is currently used every time there is a patient with COVID coming. The models are automatically launched so that they recover in a few seconds the quantitative information. So that's very doable too. But the essential step is to collaborate with the doctors, is to imply the doctors in the research. All right, so I thank you very much.
Yeah, thank you, Joris. It looks amazing.
Thank you.
Actually, we have, I think, 3 questions now in the chat. I guess the first one was from Ekaterina Brui. Thank you very much for the presentation. Could you comment what is the reason for such an extremely low reproducibility of manual segmentation, as this can affect the quality of training data?
Yes, we have an idea about why you have a low reproducibility for the trabeculations. It's because the trabeculation, maybe I can share again my screen. The trabeculation are very noisy class to segment. Stop. Okay, on this image. All right, it's first of all, it's a small region, a very small region. And that explains why, even if you have 2 segmentations that are very similar, if it's you have a shift of 1 or 2 pixels, you will move from 0.8 dice to 0.5. So that's the first reason. If you do the same with the myocardium, you do a shift of a few pixels, it will not change a lot. So that's the first reason. The second reason is that it's very blurred in general. So to sum it up, it's a difficult class to segment. It's not very obvious where are the trabeculation. So it's not, when you have a dice of 0.60, it doesn't mean it's a bad segmentation. That's we have to change our way we are thinking about dices, because we think, yeah, a good dice is 95, but that's not true. But a good dice is the one that is above or around the dice obtained with inter-observer measurements. So if you have a region you segment and you have the inter-observer dice on average that is 0.7, if you have 0.7 with your model, it's good. It means it's good. It just means that the class you are segmented is more difficult. There is more variability between 2 segmenter for segmenting this class. And can it have an impact on the training? Yes. That's why you have to be very careful with your when you create a data set. Especially if you have several people segmenting it, if you have one person segmenting it in one way, the other in another way, you will give yes and no to your model, and you will not know what runs. Like if you run with the children, you say this is true, this is false. In the end, it will be more complicated. So it's very important to select a gold standard, a politic of segmentation. Is that if you have several radiologists segmenting, they have to agree beforehand on the criteria they will use to include or not to include as much as you can. And in the last step, you can select just one of the radiologists. You can do a mean of the three, or if you select one, you ask him to see all the segmentation by the others and harmonize it. That's what we did. And after we selected one gold standard, which was the segmentation of one particular radiologist, that's one way of doing it. Or people do mean, as I said, or there is also a way of doing it. But you need to study. If your model is learning something, you need to have something regular. And was the model able to reproduce this regularity, this way of doing it? And if the answer is yes, it means the model was good. So that's how I will sum it up.
Maybe small remarks and recommendation to Joris. Thank you, Joris. But small remark for improve reproducibility, I recommend to using not intra-observer agreement, but assess inter-modality agreement. Please use CTA, computer tomography angiography, to calculate the volume of left ventricle of ejection fraction, because on CTA it's easy to differentiate contrast media in the left ventricle and non-compact myocardium. It's a real problem in MR, and maybe another tools will be helpful. It's a small remark, no more. Thank you.
Thank you.
Thank you, Vladimir. Actually, we have two more questions.
I'll try to answer more quickly.
Yeah, the first one from Anna Andreychenko. So maybe you partially answered. Do you plan to include quality control as a feedback to retrain the model, or as part of reinforcement learning?
Actually, I don't now. I'm not working. I have other project going on, but I think the possibilities with this quality control tool are indeed big, I think, and you can use them to do what was just said in this question. I didn't implement it. I'm planning to do other things. For example, to be able to have a model that would, in both, like an auto-evaluating model, which predicts segmentation and predicts, judges its segmentation, and you could train that in one step. That's an idea, but maybe in the future I will try to implement it. But yeah, it could be doable. You have to figure out in what way exactly you use the feedback to retrain the model, and that's not an obvious one.
Okay, and the question from David. If you do not use the preselection of images, what would be the real impact on the training? In other words, can you quantify each step of your survey?
If I understand correctly your question, it will not change anything on the training, because when we train the segmentation model, we train it in general with the images where there is a segmentation. So for the training, it will not change a lot of things. But where it will change something is in the inference time, where if I feed all my images to the segmentation model, it might segment zones that should not have been segmented. I need, if I start with the raw volumes, at one moment I need to select them. I need to say, okay, this is where I want segmentation, be it doing it directly inside the segmentation model as Commander et al, be it doing it externally as I did. I prefer to do sequentially, but on the training, it will not change anything, but on the inference, you will have a problem. In other words, can you quantify each step of your survey? I don't really understand what you want.
Maybe you can clarify the question.
Sorry? But maybe I answered, David, too.
I don't know, actually, I think we need some comment.
But thank you for your attention and your question. Thank you very much.
Yeah, maybe we can discuss it during the roundtable. Now let's move on to our last but not the least speaker, Dr. Stanislas Rapacchi, the CNRS Research Associate in charge of acquisition reconstruction techniques and sodium imaging for cardiovascular MRI. Stanislas' current research interest involves the development, validation, and application of novel MRI diagnostic techniques for cardiac imaging, with a strong focus on novel techniques at high and ultra-high field MRI. Stanislas, you're welcome. We do not hear you, but we see your screen.
Yes, now you can hear me.
Yes, now we can.
Perfect, thank you for the introduction. So I wanted to talk to you today about the multi-echo MRI in the body, that means in the abdomen and in the thorax, to image fat and beyond. And let's go back to the basics first. If I can move my, yes. So gradient echo sequences, everybody use them. They're very common in practice because they're fast and they're robust to motion. And that is very convenient. They can easily be extended to multiple echoes to acquire rapid spin dynamics. So they're very simple to understand. There's excitation and signal decays, but is refocused by gradients at the bottom here. And in the scale of what we use currently, the echo times range between 1 and 3 milliseconds for the first one. And the TR, which is one line, is usually 6 to 8 milliseconds. So it's very fast, and that's why they're very common in practice. But what's interesting is that they capture spin dynamics, and especially chemical shift impacts the signal and allows to separate fat and water pathways. So if you look at water being on resonant, which is the black arrow here, you can see the black arrow doesn't move because it's on resonant and it doesn't change its phase throughout the echo times, which is the scale on the bottom, the time after excitation. But on the contrary, fat has a shift in resonance, which is the chemical shift. And because of the chemical shifts, its phase accrues throughout echo time. And so after 2.2 milliseconds, its phase is opposite to the water, which is called opposite phase here in red. And so that means the phase of the fat being opposite, the water and the fat signal will cancel each other instead of add in this image. So that's why it's darker. But when you wait 4.4 milliseconds at 1.5 Tesla, there the fat and water becomes back in phase as it was initially at 0 milliseconds. And at that point, the signal from water and fat accumulates, and the image is usually brighter. And because of that, with a model is called the Dixon model, we can model the signal between being the accumulation of water and fat with this phase accrual, and we can separate these two. So if we take the in phase and the opposite phase images, we can subtract and add them, and we can get a fat image and a water image here, which allows to easily isolate both compartments, which are the fat and the water. So that is the basics of gradient echo, multi-echoes. But to get the full signal model, multiple echoes are required. And this is an example of what we do in the heart at the CRMBM. So we acquire multiple echoes. Here we acquire 5 echoes. And in color is plotted the phase of each pixel. And you can see the phase varies in space when you accumulate in time. So that means the frequency accumulates and the phase is increased and it wraps around. And so the full signal model accounts for the water and the fat again. It also accounts for B0 offsets. So the magnetic, the gross global magnetic field that is inhomogeneous. It also accounts for signal decay, which is the T2 star or R2 star, which is the opposite of T2 star. And so the full Dixon model will provide a proton density fat fraction, which is the ratio of fat over water. So it will image the fat content in quantitative measures, so in percentage here. It will also quantify the signal decay, which is the R2 star here in the heart. And Vladimir talked about it before. In the heart, it's very relevant for the iron concentration. And also accounts for B0 inhomogeneity, which is on the right image, the right map. It's in Hertz. And so it's very interesting, especially in the liver. Vladimir showed that very relevantly. When you quantify proton density fat fraction, it enables to grade fat liver. And so normal liver will appear with a dark color in this image. And when it gets fatter and fatter, the color will increase from blue to red to yellow. and we can get a measurement of the proton density fat fraction, which ranges between 0 and 30 to 35%. And at 35%, you're reaching steatosis, which is a very severe condition. And so that's very relevant and very common in clinical practice to grade this. But what I wanted to show today is that we can go beyond this. We can extend the model with an additional term, and that is the phase, background phase. That is the initial phase of the signal if we were to measure it at t equals 0, so no echo time. The phase is not exactly equal to 0. So these are the images we acquired at CRMBM, which are cardiac Dixon images, but resolved in cardiac time. So you can see the heart beating, and you can see the proton density fraction, you can see the R2 star, but you can also map this phase, the phi0 that is circled at the bottom, above at the top. And that phase is interesting because it holds information as well. And that information is relevant to very micromolecular content. And that is the QSM, so quantitative susceptibility. So we map this quantitative susceptibility from the phase, initial phase. And the processing pipeline can be very tedious. But here's an example of how it's done in some cases in the liver. So you can get all the images from the 6 TEs at the top, and you reconstruct the usual maps of Dixon model, which is the R2 star, the B0, the fat, and the water. And here you can extract a mask, a fat mask. You can derive weightings, spatial weightings, and regularize the inverse problem because it's a ill-posed problem to map the QSM, the quantitative susceptibility, from this phase. And you can get eventually a QSM map. And that map relates linearly proportionally to the iron concentration, which is very relevant for iron overload in the liver and is independent of the fat. So that measure of QSM has been shown to be very related to iron concentration. Here's an example of the images of different subjects from a normal on the left to iron overload on the right. And you can see the proton density fat fraction is not altered in these patients because there's no fatty liver here. But the R2 star as well as the QSM shows increased in these measures that is related to the iron concentration. So from a normal, you get an increase in iron and it becomes overloaded on the right. And here you can say, okay, we can see that both from the R2 star and from the QSM. So there's no real value added from the QSM here. The R2 star will be enough in this current case. But what is very interesting is that this measure, which is not very common yet in practice, in clinical practice, holds more potential. So when you compare in vials R2 star and QSM, and you add, so here in this case it's not iron, it's called gadolinium, but you add to the gadolinium collagen, which is a very important marker for fibrosis, both in the liver and the heart. So when you add collagen in these vials and gadolinium, the R2 star is biased by the collagen, but the QSM is not. So these two measures differ in that sense, is that they're sensitive to different things. The R2 star, which is very common in clinical practice, will increase, as it is shown in this diagram at the bottom right, will increase when the collagen is present. But the QSM will not. It's very sensitive to iron or gadolinium concentration, but it's not sensitive to collagen. So these two measures, when they're combined, could hold potential for more biomarkers than is currently used, with the same acquisition as the acquisition that is performed clinically. So that is what has been done recently in this paper, and remains to be proven in a larger population. But here's the normal subject with the R2 star and the QSM. So it's a normal subject, so there's really nothing to see. But in a fatty liver patient here with a moderate iron overload, you can see the R2 star increased, but you can also see the QSM increased. But what's interesting is that there's a gradient of R2 star throughout the liver. And the liver here is very bright. The R2 star is very bright, but QSM is not. And it suggests that there might be an increase of collagen and a suspected fibrosis in this patient here that could be isolated with the distinction between the R2 star and the QSM. So these are biomarkers that are unexplored clinically yet, but that are understood physically, and that remains to be explored in the clinics. And again, this is the same acquisition as the one we use or everybody use in clinics. So with that, just wanted to make a short presentation because I'm the last one. But thank you for the intention, and I welcome any question regarding the prospect. Thank you.
Thank you, Stanislas. Colleagues, any questions? Yes.
So I just wanted to clarify things a bit. So you take fat fraction into account by fitting the phase in the first equation you showed to the data that they have, right?
Yes, I can go back, but the full model that is here accounts for R2 star and the fat. So it separates both, and the R2 star is corrected for fat. And is relevant to the actual tissue decay and iron when there's iron present.
What is the range of the TE that you're using here?
The TEs are written at the bottom of the images.
Up to 9 milliseconds, right?
Yes, because it needs to be fast. We stay in a short range of TEs, especially because it's cardiac. In the liver, it wouldn't need to be so short, but in the cardiac realm, we need to make short echo times.
In the cardiac region, do you need to do any phase unwrapping?
Yes, phase unwrapping is necessary because around the lungs, there's a very fast B0 changes. And so phase unwrapping is necessary usually, but there's multiple methods available for phase unwrapping.
Any particular ones that you have success with?
The latest one is called Romeo, like Romeo and Juliet, and you can find it online. It's open source.
Okay. Thank you.
Seems there is no more questions.
Great.
Or somebody type in the chat. So maybe we can move on to the round table where we can actually discuss some other questions or just share some ideas, comments. So everyone welcome to participate.
Yeah, maybe I would have a comment about the last talk about Stanislas. I think that typically the kind of processing he was presenting is based on a conventional sequence. And this is definitely what we would like to do, to use a common sequence, an advanced post-processing, and to translate multiple metrics to the clinics in order to propose to the clinician new tools in order to assess the disease. So I think that's really a nice approach of that we could use for different clinical applications.
Okay, we have a question in the chat. Stanislas, it's for you, I think. Do we have tools?
So I take back the microphone. Yes, there are tools for QSM. There's actually multiple ones. And there's an interface that's called SEPIA, S-E-P-I-A, that you can find online that provides an interface for multiple tools, for multiple QSM tools. Each tool needs to be downloaded after registration, so they're not provided directly. You need to download them, register for each of them separately, and then you have an interface to process QSM. It's called Sepia. You can find it on GitHub. And it has links to download each of the tools it helps to interact. If you type Sepia and QSM online and GitHub, you will find that. That's why it's very interesting. But one thing is that you need, for QSM, you need a proper phase. And just to be clear, on neuroscanners, on VB17 and VB19, the phase that is provided by the scanner is inaccurate and cannot be used for QSM.
So is it a hardware limitation that isn't there, or?
No, it's a software issue that was unknown at the time it was created. The software was created. It's a mathematical problem that is what was ill-posed at the time. So you need to retrieve, ideally, you need to retrieve Twix data, so raw data, and reconstruct the phase yourself.
Okay, so it's possible to.
Yes, but you need the raw data. Usually, if you output the phase from the scanner, you are unlikely to be able to process it. It will work on maybe in the liver, but it will not work in the heart, where the phase accrues very rapidly and changes very rapidly. In these cases, it will not work. Maybe in the liver. I know in the muscle it works, in the legs, for example, because the phase is very homogeneous and slow to change spatially, but not in the heart, and maybe not in the liver either.
Stanislas, can you repeat the time the operating system with which it doesn't work for the phase?
The VB17 and VB19, the VB line had an implementation of phase calculation that was incorrect. Okay, so do you think they're gonna fix it? No, they fixed it in the VE line. Okay. And further. So in our recent scanners, there's no problem. The phase can be used directly. Good. Okay. The old scanners have the issues. Mm-hmm.
Maybe I have a question to David. David, during my talk, you mentioned this idea of the implementation of some artificial devices for heart spectroscopy, phosphorus, right?
Yes.
Yeah,
maybe can add a comment, because I didn't mind that he was saying with Frank that doing spectroscopy was very critical, phosphorus spectroscopy for heart, and I was thinking that maybe with the pad, the method, you can increase the flip angle right in the heart. That can be maybe useful for heart spectroscopy.
But now the problem that you do not have a specific coil, or the coil sensitivity is poor for this spectroscopy. So what kind of problems you have now?
Frank, do you want to comment on this, or should I do it?
No, go ahead. Oh, Frank, yeah.
Just for a short explanation. So in phosphorus imaging or any other X nuclei, we use a local transmit coil, like we do at 7T, for example. And these transmit coils are not very efficient, so they provide a very inhomogeneous transmission, so B1 plus. And because of that, it's very difficult to do any quantitative measurement or even imaging deep in the heart, because the field is not sufficient to provide enough excitation. And so any pad or any passive mean to improve the B1 plus of these coils will greatly benefit to these applications.
Stanislas, could you remind me what's the frequency of the phosphorus at 3T?
Yes, that's a very good question. It's very low.
I wanted to ask also.
Yes, it's. I think Frank will give us the exact numbers, but it's in the range of. I think it's in the range of 14.
It's about 3 times lower than the proton.
Yes, exactly.
5 times lower.
So it should be about about 20 or to 30
Yes,
megahertz.
I think it's 27 on a 1.5.
okay. I'm not sure actually that it's possible to realize with the electric pads, but we definitely can think how to realize it with metamaterial, because with metamaterial we can create, let's say, different effective permittivity.
Do you know?
Yeah, but
sorry.
I think it may be interesting then for the higher fields, isn't it?
For high, you mean for 70?
Yeah.
Okay.
And
there's a real power problem, actually.
Mm-hmm.
There's also a question from Dmitry Kupriano, but Frank or Stanislas, do you know what kind of coils do you use for excitation in there? What's the configuration of the coils?
In which situation you mean?
For phosphorus spectroscopy on 3T, what's the coil structure inside? Is it just a loop coil or some kind of different configuration?
There are different models around, and we currently use it's actually two coils, one for transmit, which is a single loop, which is a bit larger than the receive part. And the receive part is composed of two loops that overlap, if I understood this right. We also had a quadrature butterfly coil on 1.5 Tesla. That was an old coil made by Siemens. And that was probably the best coil we ever had. And no one makes this anymore, but if you
that was the thing that I was thinking, because I don't know if Pavel Serogin is online with us here. He is very fond of those Siemens combinations of loop and butterfly coil, like loop and 8 shape, which combines to a butterfly coil. Maybe it would be, this construction would actually increase the homogeneity of your excitation and reception, even in 3T.
Yes, it may, and that would really be an interesting
We can probably ask him to.
As long as but you know, for phosphorus, as we have always partial saturation, you know, for increasing the scan efficiency, we don't scan with full relaxation time. And therefore, all the metabolites are saturated. And they are saturated, you know that, by flip angle and repetition time. So the repetition time in the heart, if your ECG gate, is variable. And the flip angle depends on the position. And if you don't know the B1 field at transmit, you have a problem. Because the PCR and the ATP and all the different components of the spectrum don't have the same repetition times. So it will not only affect the amplitude of the spectrum, but also the ratios between the peaks. And that is what makes, especially in the heart, all this spectroscopy so difficult. So if your coil can, or your pad, is able to make it more homogeneous at the excitation, that would already be of great help.
We can try with the pads.
You probably can try with the pads. But it should, I guess those would be the non-resonant pads, because the frequency is so low.
Yeah, but at 70, I guess the phosphorus frequency
it would be about 120 or something.
120, yeah. That means if we can try the electric pad maybe.
Yeah, the ones that we use for 120 at 3T.
Yes, and then there is a problem of measuring a B1 field at on phosphorus because of the low signal intensity. You know, you can't just do imaging with it. One option would be to go to a lower field and do the same thing on proton with the same pad and the same coil on the proton frequency at 1.5, and then go to phosphorus at 7T or something like that to get a correct B1 map. Or other option is to use a very concentrated phosphorus phantom that resembles the body, and then hope that it will be the same in all patients and volunteers when you replace the phantom by a real body. So that's what we currently did at 3T. It's like use a pre-measured B1 map for doing all the corrections, and apply that one to the local voxel position that we obtain for from spectroscopy. And so for characterizing your activities or your improvement with the pad, that will be quite lengthy exams, I think, on a phantom, but it will be very difficult to get that on a real body. So be aware of that. It's just
because of the so it's really hard to, because I haven't done a lot of phosphorus imaging myself, so it's really the signal to noise is very low with phosphorus, right? In nature.
Yes, you can get voxel resolutions of about 2 centimeters or something like that.
So in natural abundance, it's imaging is pretty much impossible, even at 70.
Yeah, absolutely. You need a CSI sequence, chemical shift imaging sequence, and that has very low spatial resolution, and it takes about half an hour, let's say. If you get for a B1 map, you know, it's not for a cardiac CSI exam. You can go with less than that because you can accelerate things and you can use lower repetition times, and but then you don't, you're a little bit vague in everything that is quantitation. And so if you really want to count on your signal amplitudes, it would require a longer exam, I think. Yeah, but it's still possible. I mean, we did it with CSI on a big phantom, and then hope that that field would apply to all situations.
Yeah, we need to keep in mind that, you know, when we do proton spectroscopy or imaging, the concentration of water is something like 100 moles per liter. But when you switch to phosphorus, the largest concentration would be something like 30 millimoles per liter. So you can see the difference, and that explains why the images you do with proton are not the same quality as the one we do with phosphorus.
We also have a comment, from Dmitry in the chat that very often the power of adiabatic acquisition is insufficient in phosphorus MRS. So, and it will be interesting to discuss.
And also we have experience working with 1.5 Tesla phosphorus spectroscopy in Symphony installation 10 years ago, and most disadvantage from clinical point of view, it's small deepness ability, penetrating and deep of the liver, and we assess only 1 or 2 segments. And also volume, it's very big. It's 2 by 2 by 2. It was 8 cubic centimeters per volume. And examination, it's so long, and we need different amplifier for phosphorus spectroscopy. It's not possible in our situation in Almazov Centre.
Yeah, I think right now all the systems are equipped with an X nuclei amplifier, and so the only thing you would need is a coil. And you're the guys for doing this.
So
I wanted to say that regarding the adiabatic acquisition, the pads will allow to reduce SR a little bit.
A little bit, yeah.
So probably the power can be increased. Yes, then this should be a different point to study?
Not much.
Not much. No, I guess it was around 20% or something like this. No, not so much significant as the metamaterial-based coils.
Yeah, I think at 70, SAR becomes an issue even with phosphorus. At 1.5, I don't think it's an issue actually. Even at 3, I think it's not so.
Regarding the adiabatic pulses, just what Dmitry has written, that the power of adiabatic acquisition is insufficient. So probably it's an issue.
Yeah, you're right. You may then do things like really fancy adiabatic excitation pulses, like those composite AFP pulses, Burr4 and things like that, that are pretty much demanding on SAR. Yeah, so that's another perspective that's interesting, I think.
Yeah, I see now actually maybe 2 ways we can improve the transmit efficiency of the current coil by using the pads, or we can maybe try to think about creation of some I don't know, artificial transmit coil based on materials or ceramic, which will directly localize the B1 plus in the heart. That also was the idea which we discussed after your initial presentation.
With Losha, I think it was after Vladimir's presentation that's an interesting thing that actually we can try to localize the field in the heart, but that would be not for phosphorus. For phosphorus, especially at 3T, I think it would be.
It will be challenging, yeah.
It would be challenging.
But for 70, we can try.
For 70, you're right. For 70, we can probably have the same solution for 70 phosphorus and 3T hydrogen.
Yes.
Because the frequencies are quite similar.
Do you have segmentations of these images?
Of which ones?
Of which one?
The one you are speaking about, where you want to apply the same technique.
Joris, what you would do then is like segment the proton images and apply them to the phosphorus CSI maps. So
okay.
I think there's no point in directly segmenting phosphorus images because the spatial resolution is so low.
It was not.
You know, they look a little bit like PET images.
I see, but it's just as
you can still try
classified images. Just a way to. I didn't use the segmentation to detect and to classify the slices, but I use them as a direct way to organize the images into 2 folders. And if you don't have the segmentation, you need to do it manually, and that's why I asked.
No, but I think automatic segmentation of a reference proton image data set would be of great help there, because it makes the post-processing then much easier. And we have tools, especially developed by Jan Le Fur, who's also part of my lab, who would be able to provide phosphorus integrated spectra integrated over a segmented region. And so I think segmentation is still a useful tool here, but then on proton.
So any other questions to discuss?
I have a question on, I think on Vladimir mentioned that there would be quantifying extracellular space would be an interesting topic. Because I don't remember, is there any particular techniques that we can use to assess extracellular space with currently, because as far as I know, it's only relaxation measurements that can do that. Can someone correct me?
Yes, assessment of extracellular volume and intracellular volume is accessible to using T1 mapping technique. It's we don't have a technique to do on the heart and just with on the liver, but in literature you can meet maybe correlation between late gadolinium enhancement for assessment of the scut in the myocardium and also with T1 mapping, and with equation we can calculate extracellular volume.
So a combination of DCE and T1 mapping would be
on basis T1 mapping. Via equation you can calculate extracellular volume and also build a map for them.
Okay, that would be.
But only it reaches experience, not so.
I should probably take a look. If you can send me the link to something about that, that would be interesting to read about. I think there is some proposition or some techniques on quantifying the extracellular volume on something like UTE sequences and T2 star mapping. Also with some something like called double quantum filtered imaging, but I'm not really a specialist in that. So there might be some additional techniques about that.
Let's change the link.
Something about the exponential relaxation.
Yeah, maybe.
Colleagues, maybe somebody in the Zoom have some questions.
It's too late and maybe we're tired. So many information. Thank you everyone for discussion, and especially for Stanislas. He leave us, but he with us, and it's very, very interesting, and and the radiologist must try and compare the data obtained by QSM and clinical data of liver assessment, and compare with conventional pulse sequence T1 and T2. It's very, very interesting and very, very promising. Thank you, Stanislas.
I don't know if we have no further questions. David, maybe you can make some closing remarks regarding today's meeting.
Yeah, I think that at the first kickoff meeting, we talked about multiple things, and I'm pretty sure that we could think about organizing the next, it won't be a kickoff anymore, but the next meeting to keep on exchanging about all this stuff. As we have heard, there are issues coming in, the one for phosphorus spectroscopy, for instance, that could be of very much interest. And I think we've got a nice group to work together. We've got clinicians, we've got experts in MRI, experts in biology. We can still think about growing up as a group and to include additional people. We talk already about having some people with an expertise in artificial intelligence that could be of interest as well. I was quite happy about the discussion I've heard today, and I can only hope that this quality will remain at the same level for the next meeting. I hope the situation will be resumed quite rapidly, so we can meet together in the same place. But I thought that even doing it remotely, the quality of the exchange was quite high, and I'm quite happy about that.
Thank you, David.
Thank you.
So anyone would like also to say some closing remarks? Maybe.
Will the presentation be available after this?
Yes, actually we have a presentation available and also recording available. And if you would like to have it, I don't know, maybe I'm of course will share it with the project participants. But if somebody else would like to, I don't know, join us, collaborate with us, or just have access to the recording, please write me an email. I will leave it in the chat. So yes, here is my email. So I would like also to thank all participants for coming. I've seen that we have many external people today, and it's very cool. So I think we have a good discussion today, and all the presentations was very interesting and very useful. So as David already mentioned, I hope our next meeting, scientific meeting, will be offline here in St. Petersburg, hopefully in summer when the weather will be nicer than today. So thank you, all of you, once again. And so if there are anything we didn't discuss, please email me and I will resend your message to any project participant. I will share with you some information.
Thank you very much, Alena.
Thank you.
Thank you very much to all of you.
Thank you.
Talk to you next time.
Yeah.
Bye-bye.
Bye-bye.
Thank you.